In this video, I'm going to be going through how to do bending, but we're going to do some more complicated questions. We're going to look at shear force and bending moment diagrams. Now, I'm going to try and teach this this concept without using, without going into too much theory, and to try and build up using past HSC questions. So the first question I have here is from 2013, and what it says here is that we have a laminated beam. It's 70 millimeters wide, 300 deep, and it's got a span that is 16 meters long. It's simply supported in each end and it's loaded as shown. Okay, so that's fine. We're happy with that. Now, the reactions are very, very easy for us to solve, right? If it's a total of 10, it's symmetrical, so it's going to be half on each side, 5 on each side. That's pretty easy, right? Now, the thing is, we've said in the past that we need to find the maximum bending moment. We've said that often, especially if it's symmetrical, often the maximum bending moment will be in the middle, right? So if we took that approach, let's just try that approach for the moment. We're going to say we're going to take moments about x, and we're going to say that this must be 5 kilonewtons, and this is also 5 kilonewtons. Are you okay with that? What would our bending moment be at point x? If we could take the left-hand side or the right-hand side, it's going to be exactly the same because the thing's symmetrical, right? I'll demonstrate that really quickly. So if I say over here that I'll use the space. The sum of the moments about x equals 0, and we just take the left-hand side only. What we're going to have is we're going to have 5, and what's the distance? It's going to be 8, half of 16. Yep. 5 times 8. Is that going clockwise or anti-clockwise? It's going about x, it's going to go clockwise. Yeah? Okay, so it's positive. And then here we have 5. Is this 5, is it going clockwise or anti-clockwise? So it's going to be anti-clockwise. And it's about a smaller distance, so it's going to be 3. Right, which what we get there is we're going to have we could use fractions here, sorry, factorization here, just to say, well, 5 minus 5 is going to be 25. Right, so it's going to be 80 minus 15, sorry, 40 minus 15, which is 25. Okay, 25 kilonewtons, and it's going to be going clockwise. If we take the right-hand side, let's say over here, right, it's going to be the same thing. Sum of the moments at x equals 0. Clockwise is positive. If we take the right-hand side, we're going to have 0 equals minus 8, 5 times 8, plus 5 brackets 3, which is going to give us minus 25 kilonewton meters. Right? That should be meters. So the idea is that the bending moment in the middle of this thing here is going to be minus 25 newton meters. That's its maximum bending moment on either side. Yeah? Now, that's enough for us to probably solve this question, but what we're going to look at is we're going to see, it says draw a shear force diagram and a bending moment diagram for those values. Okay, so what they want us to do is, this is to find the maximum bending moment. So remember, bending moments are measured in Newton millimeters or Newton meters. We're going to use kilonewton meters, and then we're going to convert it. Which, where I probably should have started is, okay, let's go back a step. I'll write that down just so I don't forget it. M max equals 25 kilonewton meters. Okay. What are the 3 things you need to know in this course to not embarrass me?
Cement is made of concrete is made of cement and aggregate.
Excellent. Yep.
Steel is over 300 megapascals.
Yep. And the second one?
Stress equals force over area.
Unless it's 2B, which is bending stress equals my over I. Okay, so we need to know these letters. We need to know M, which is maximum bending moment, which we have there. But we're going to convert that, and we're going to say that is 25 times 10 to the 6 Newton millimeters. Are we okay with that? Yeah, we're familiar with that. Okay. We then need to find I, or I bar. What's that? In this case, so Y bar is the depth from the neutral axis to the extreme fiber. In this particular case, YC equals YT, which equals D on 2, which is Y equals 300 divided by 2 equals 150. Are you okay with that? Okay. I think people are happy to accept Y really quickly. They just don't understand what it is. And it's the distance from the neutral axis, the part of the beam that's neither in bending or in compression, and it's the distance from that to its maximum compression or maximum tension. In this case, maximum tension and maximum compression, they're the same distance, so it doesn't matter. We can just use half of D. Okay. And then the I value is the I value given. It might be given on the next page. Now what they've asked us to do instead is they've asked us to draw a shear force diagram. So I'm going to show you what a shear force diagram looks like. We haven't looked at those yet. A shear force diagram is kind of a story of the forces, right? Once upon a time there was this beam. I'm going to make this a little bit smaller just so I can get the bending moment diagram on there. Okay, once upon a time there was this beam, and it had a reaction of, what was our reaction? Look at the beam, let's do it again. What's the total force? 10. Is it symmetrical?
Yes.
So it's going to be half of 10 on each side, 5. So what happened? Well, we went up 5 newtons, right? 5 kilonewtons. And then nothing happened for a while. The beam just went dum-de-dum-de-dum, and then suddenly it went down another 5. And at that point, it was at 0. And it kept going along, dum-de-dum-de-dum, dum-de-dum-de-dum. And then suddenly, another 5 came along. Oh, and it was bad times for this beam. This beam was like, oh man, things have never been worse. But then at the end, a reaction came along and saved the day. And you know what? It ended up back at 0. Yay! Okay, and all beams that are in equilibrium will end back up at 0 at the end. They might have an exciting roller coaster ride, but they always end up back where they started, right? Now, here we have a bending moment diagram. How a bending moment diagram works is we're going to show what the bending moment is at every location. Now, it's a bit annoying to find the bending moment at every single location. Like, we've already found the maximum bending moment, which we've already said was that. But what we really want to do is we want to sometimes get bending moments at different points. So let's have a look at what's the bending moment at, say, here and here. And look, maybe just chuck in one more. We've already done that one as well, right? So let's just do this one really simply. We know that the left-hand side equals the right-hand side. So what's the bending moment diagram here going to look like? It's just going to be 5 times 0.25, right? Okay, so 5 times 0.25, 5 times 0.25 equals 12 and a half, right? Which is about half of this number. Okay, the next point, let's go here. What's it going to be equal to? At this end, what's the left-hand side going to be equal to? It's just going to be 5 times 5, right? If we're just looking at the left, if we just go to the left-hand side of that force, right? We're not including that force. We could include that force, but if we included that force, what would we be multiplying by? 0. Yeah, so at this point, let's give it a letter. We'll call this J, right? At point J, which is here, we'll say sum of the moments at J equals 0. We're just taking the left-hand side. We've got 5 times 5 meters away. Or actually, we should really write it like this. We should write LHS equals 5 brackets 5, and then I have that's going clockwise, and then I have 5 brackets 0. It doesn't matter what my sign is because the perpendicular distance to this force at J is 0. So it's not positive, it's not negative, it's just 0. So what are we going to have? The sum of the bending moments, the left-hand side is going to equal 25 kilonewton meters at J. So let's keep drawing that up. Okay, and then we've already found that the point in the middle looked like that. Yeah? Now, this thing's symmetrical, so it makes sense that the other half will be symmetrical as well. Now, I'm going to tell you a little secret that can help you to solve these things. Let's call this block here block A, and this block here block B. The bending moment, you can calculate every single step along the way, and I remember doing that, right? I remember doing that all the way through uni. And then, somewhere along the line, someone said to me, you know that you can just take the area under the curve, and it's going to be equal to it. And I'm like, that's genius. It just made my life so much easier. And then after that, my professional life, that's all I did. And I've talked to engineering studies teachers, multiple engineering studies teachers who did not know this little trick, right? So if I take this area, this block A, what's the area? It's 5 kilonewtons is how high it is, 5 kilonewtons, and it's 5 meters wide. It's 5 kilonewtons high, and it's 5 meters wide. So what's its area? 25 kilonewton meters. 25 kilonewton meters. And then there's nothing here. So it just keeps on going. We don't add or subtract anything. And then here we have minus 5 kilonewtons. So what do we have here? That's an M. 5 times 5, but it's minus 5 is going to be what?
Minus 25.
Minus 25. So what we do is we take 25 minus 25 gives us 0. And that is our bending moment diagram. And that's the story of how much bending there is in this whole beam. Yeah? Even though nothing's happening here, it's like I've talked before about how when you see the pipe sticking out of the electrician's van, and the pipe bends, and you think, well, it's interesting that the maximum bending, is actually happening here. This finger, well, it looks like it's bending the most, but in actual fact, it's got the least load on it. The worst part, the part that's doing the most work is right up here where it's touching. And that's what we can see here. You can see even though there's no load here, it still has all of the bending happening. And this is where the maximum bending, that whole area is still under maximum bending. Yeah? So this is the part that's most likely to fail. This is the part that needs to be reinforced. Or this is the part that we don't want to drill holes into. This is the part that is the strongest and that needs to be that needs the most attention. This is where it's most likely to fail. So, okay, we've now drawn our diagram. I can now skip this and move on to the next part of the question. Okay, determine the second moment of area if I is equal to this. So they said if I equals 157.5 times 10 to the 6 millimeters to the power of 4. Okay, we just plug the numbers in the equation. Real easy here. Okay, so we say sigma b equals 25 times 10 to the 6 times I, which is 150, divided by 157 times 10 to the 6 equals 25 times 150 divided by 157 equals, because these cross out obviously, is 23 megapascals. Okay, 23 megapascals is pretty low, right? For steel, that would have a huge factor of safety. For concrete, that's okay. That's probably where we'd expect the load to be for concrete. Okay, so we're happy with that. That's our question. That was worth a total of 6 marks, 3 and 3. On to our next question. We're going to do 3. Okay, so this next question, they've given us the shear force diagram, but I'm going to help you, but I want us to build up the shear force diagram ourselves. Okay. This question is only worth 1 mark, and you can tell that they've helped us by giving us the shear force diagram. They've already given us the reactions. What do we call this little part sticking out over the top here? Starts with a C? Cantilever. Right? right? Sticking out over the top, right? Cantilever to extend past the reactions. Yeah. Now, when we have a cantilever, do you see how that gives us this unusual graph? Right, this part coming up here. We're going to see how that affects the bending moment diagram when we draw a bending moment diagram. Okay, what they've done is they've already given us the reactions. Well, I guess it's multiple choice. It's a relatively hard multiple choice. It's at 15, so it's getting to 3/4 of the difficulty of a multiple choice. But they've also given us the shear force diagram. So let's go through the story. Once upon a time, there was a beam. And it started off by, like the roller coaster, tick, 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 tick. It went up 2 meters. And then it went across. Nothing happened. And then there was a drop, 3. It went 2 minus 3 is? -1. It went across. Nothing happened until 3 dropped down again. -4. And then tick, 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 tick. Whoosh! It went up. All of a sudden, 9. It went from -4 up to 5. And then it went across, tick, 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 and then went down. One last down, and see how it finished at 0? And the end points, the start and finish, have to equal 0. Because if they didn't, the reactions wouldn't work, right? It wouldn't work because, remember, the left-hand side has to equal the right-hand side. And there is no right-hand side over here. There is no left-hand side over here. So for those have to be 0 at the ends. Now, I don't have any space to draw the maximum bending, the diagram, but I'm going to draw for you now what the diagram would look like. And I'm just going to draw that in the middle here. There we go, that's where I'm going to draw my bending moment diagram. So I could work this out. And you know what, the first one I'm going to work out. If I took the moment at A, at location A, if I took the sum of the moments measured at A equals 0, and if I took the left-hand side, I'd have 2 times, well, let's see, left-hand side equals 2 multiplied by 4 clockwise minus 3 brackets 0 equals 8 kilonewton meters. Are you okay with that? Now let's have a look at our diagram. Here we have 2 times 4 meters equals 8. I'm going to write the distances here just to help us. 2, 4, 2. Now that we've proven that, we don't need to do that every time. We're just going to say this here is 8. Okay. Then we have 2 times -1. So what's this? The area of this block? -2. So then we're going to go 8 minus 1 times 2 equals 6. So that's where we're at. Okay, then we've got this block here. Well, this block here is 4 minus 4, right? So what's that going to give us? Okay, so what we're going to do is we're going to go 6 minus 16 is 10, yeah? Minus 10. So what we write here is we write 6 minus 4 brackets 4 equals minus 10. Does that make sense? And then finally, just to check that it all works, we have 2 times 5 equals? And 10 minus 10 plus 10 equals 0. Pretty cool, huh? Now, what we can do, each of these is kilonewton meters. And what we can do is we can look at that diagram. If we have a shape like this, so this is positive and this is negative. If we have positive and negative, what that means is, and what I'll say is that it'll also give you an idea of how the thing's going to bend. It looks like the opposite of the shape. So, well, it's actually going to go like this, like that. Yeah, that's kind of how that thing's going to bend. Do you see how it's opposite to the shape? And wherever we have a cantilever, we're going to have something like this. We're going to have a negative area. Now, sometimes people write positive, they write them the opposite way, so it matches the shape of the deflection of the beam. Yeah, it's up to you. We did it this way, that's fine. That's very, there's no real consistent convention there. But, a lot of people do it both ways. Now, what we're going to look at is what is the maximum bending moment in this diagram? What's the most extreme moment in this diagram? Minus 10. Yeah, so if we're talking about maximum bending moments, we'd actually, if it was a steel section, we don't care if it's maximum or minimum. If it's steel, we just treat whatever it is, absolute values is the value that we take. Yeah, so the maximum bending moment is minus 10. Yeah, for this diagram. But for concrete, it's a bit more complicated. I'll just quickly talk about, so the answer I'm pretty sure that they want us to give is C. But what I will quickly talk about, I've lost the diagram, but it was something like that. What I will talk about is the maximums always take place, see where we cross this axis? That's where the maximums are going to take place. See how we cross the axis here and cross the axis here? So that can help us that if you wanted to save some time and not have to do this whole diagram, what you could do is you could just calculate A and compare it to calculating C, and that would help you to get the answer as well. Because if you just took those values, and remember, we don't have to take the left-hand side. If we're lazy, we could say take moments at C. We could just take the right-hand side. So we could say the sum of the moments clockwise at C equals 0. We could say RHS equals, what we've got here, we've got 5 times 2 equals, and it's clockwise, equals 10. Yeah? So if we take moments from C, and we just take the right-hand side, we're going to get 10. Yeah? And that will give us our answer as well. The thing is, if you're designing for concrete, here's how concrete works. With concrete, and I'm only going to say this just because I have questions that have sort of discussed this. If this was a concrete beam, I've drawn a bit wonky, but forgive me. What we would do is we'd have steel running along the bottom of the concrete beam. Even here, we'd still have some. And then we'd only put steel at the top of the concrete beam there, likely. A bit complicated because steel, remember, steel always goes on the bendy side, on the side that's being stretched, that this is where the tension is, yeah? So we put steel where the tension is. So we put some steel there. Now, if we have a really small beam, we might actually put steel through the whole thing, but we'll put more steel there, and we'll put more steel there. We'll put extra steel there. If we had to squash the beam, if the beam has to be really little, you had to make it a bit stronger, put a bit more steel in there. So that's something we can do. And this is why do we use bending moment diagrams? Well, we use them to check that the member is strong enough to withstand the loads. In this case, the bending loads. So what do we do? What do we do if it's wrong? What if we say, hey, look, this bending is too great? What can we do? We could add more steel, right? We could change the material. We could rearrange. We could redesign, right? We could say, hey, we're going to have to put a wall in here, right? We could redesign. We could make the beam deeper, or we could change the materials. Yeah, so there's some of the different things we can do. And that's the purpose of having these diagrams. That's why they're there. So I'm pretty sure the answer they want is C. Okay, this question here, they're asking us to match the correct bending moment diagram. Again, this is a multiple choice. This is from an old multiple choice. This is from 2009, so this would have been the hardest question of the paper. So, we don't have a shear force diagram to help us. So let's draw up our own shear force diagram. Once upon a time, there was a beam, and it went up 9.4 meters. 9.4. And then it went across a couple of meters, and it went down 9. But it wasn't enough for it to go underneath the axis. It still had 1.4 left. But then 12 came along, and it went down, down, down. How far down did it go? 9.4 minus 8 is 1.4.
Oh, sorry, it's supposed to.
Yeah, and then 12 minus 1.4, it went down 10.6. Oh, and of course it had to be 10.6, because otherwise it wouldn't balance. Now, if I was drawing a diagram for that, what would that look like? Well, my diagram, I'm going to draw it up here because I'm running out of space. This is 3.5 meters. This is 3 meters. This is 3.5 meters. So what would that look like? 3.5 times 9. 3.5 times 9.4 equals 32.9. And then I'm going to go across with a little bit of down. It's going to slide down a little bit. So it's going to be, so how much is it going to slide down? It's going to slide down 3 times 1.4. 4.2, it's going to lose 4.2. So I go 32.9 minus 4.2 equals 28. That's probably a little, it's not to scale, but it doesn't need to be. And then I'm betting that this part here is also going to equal 28. 3.5 times 10.6 equals 37. Oh, this is positive. Whoops. Hey, but you know, I didn't need to look up the answers to see that. I knew that if it didn't equal 0, something was wrong. So what I looked at is, oh, this is actually going up because it's above the line. It's positive. Yeah? So what's this going to equal? It's going to equal 37.1. And I know that because this has to close. Yeah? If it doesn't start and finish at the same spot, it's not going to work. Now let's have a look. Do we have that answer here? A, B, C, or D? A matches. Now, Copeland, now we could, the answer, I think there's an argument that this could be treated as correct, right? I think that there's a way that you could say that that is correct, but, and that is what I really do, oh, no, okay, sorry. This couldn't be correct. What could be correct is this. It could be correct if it had done that. Yeah, then it would have been correct. Okay, I take that back. It has to either be that or that. So B cannot be correct. Yep. Okay, I'm glad we got that. So, Copeland talked a lot about how to figure out bending moment diagrams, and we're going to look at in the future how bending moment diagrams look when. See how in these questions we only have point lines. We only have things just going straight up and down. But it is possible that you can have instead lots of little forces. Well, that's how we draw them, right, as engineers. We just draw them, but lots of little forces. See, if you draw that fast, it just looks like this. Yeah? Lots of little arrows. And if you do that, you get different looking diagrams. But we're not going to worry about that today. We've just covered 3 questions. And we've introduced how to use bending moment diagrams and shear force diagrams. We also know why we use them. Yeah, to find the back. Just to remind you, the key point is when we use our equation, we would use this for our maximum bending moment. Yeah, because we're not interested. Typically, we're not usually interested in the bending moments at lots of locations. We're usually just using it to find the maximum bending moment. But when we talked about earlier, if we were putting steel in this beam, we might put a little bit of steel the whole way, and then we'd add some more steel here, and then we'd add it all the way through. And then we'd add the most steel there. Does that make sense? Yeah, we could add more and more steel. If you're putting a steel beam in, you probably just use the beam that suits the biggest thing. Okay, that's great. We're done for today.